Hello everyone, and welcome back to this Nanophotonics and Plasmonics course. In this video we will derive the dyadic green function from the scalar green function. So in chapter 2 we introduced this green tensor or dyadic green function which relate a source which is positioned at R prime, which can be a current density distribution with the electric field calculated at a position R. And we showed that this is expressed as a function of the scalar green function with the following expression, where I is the unit tensor or dyad, and G node is the scalar green function. So this scalar green function, G node, is not a tensor, as opposed to the tensor G. G node is not a tensor and is taking the form of an exponential ik and r minus r prime. So the distance between the source and the position where we calculate the field, and then 1 over 4 pi r minus r prime. So for simplifications, we're going to introduce this capital R vector, which is r minus r prime. And we're going to just introduce r as basically the norm of this vector, or in other terms, the actual distance between the source and the location where we evaluate the local electric field, the electric field. So let's rewrite this green tensor. So now we can just rewrite the green tensor as a function of the vector capital R. That's going to simplify a lot of things. We have this expressed as the unit tensor plus 1 over k square gradient of the gradient of this green scalar green function, which is exponential ikr over 4 pi r. So what we're going to be doing right now is basically just try to expand this, apply those operators in the bracket onto this scalar green function, and we're going to just calculate this piece by piece. So the first thing we're going to be doing is actually calculate the gradient of our scalar green function, of in other words, the gradient of the exponential ikr over 4 pi r. So let's do that. So what we have here is just a fraction, a quotient between two functions, and an exponential in the 1 over r, or product of function. So let's calculate this gradient, which is just a special derivative with respect to r. So this leads to r times the gradient of the exponential minus the exponential times the gradient of r, and then we have 4 pi r squared. So this is just a simple derivative of those two functions which are on this fraction. We can expand that a little bit, calculating the gradient of the exponential. So we're gonna be left with this ik r exponential ikr, and then we have this gradient of r that show up from the derivative of the exponential, and then we have the second term, which is exponential ikr, and then we have the gradient of r that we leave as is, and at the denominator we have 4 pi r squared. We can just factor out the exponential in the gradient of r with a 4 pi, and then we're going to be left with ik over r minus 1 over r squared times the exponential IKR over 4 pi gradient of r. So this is what we obtain when taking the gradient of the scalar green function. Now the second step would be to take this second gradient on top of this. So if we take the gradient of this gradient of the scalar green function, then we apply those derivatives on top of this this expression, which is I'm gonna frame that in blue. So this is what we're gonna be taking the gradient of. So we have a product of three functions. So we have the function which is in the parentheses here, where we have the 1 over r and 1 over r squared. We have a function with the exponential at the center, and then we have this function gradient of r. So if you take the gradient of this product of function, then you just basically can go from there. So let's take the gradient of the parentheses. So when you do that, so you can put the ik over r minus 1 over r squared on a common denominator, and then you can take the derivative with respect to r on top of that, and you should be left with 2 minus ikr over r cubed gradient of r. And then if you look at the other two terms, the exponential ikr over 4 pi, and then the gradient of r remains the same. So you see that we have now a second gradient that shows up because of the derivatives. So that's basically taking the derivative of the first term, the first function, into the parentheses. Then we have the parentheses that remains the same, and then we take the derivative of the exponential part. So we can have ik that will come out from the equation, and then with the ik from the parentheses, then we're gonna be having negative k squared r squared minus ikr over r cubed, and then we have the exponential that is left from the derivative. We have also a gradient of r that shows up when you take the derivative of the gradient of the exponential, and then we have the original gradient of r that remains. And finally, when you take the gradient of r, the first two functions remain unchanged. So we have 1 over kr squared minus r cubed exponential ikr over 4 pi gradient of r. So now we can just do a little bit of cosmetic. We're gonna actually factor out exponential ikr over 4 pi r, which is the scalar green function. And then we're gonna be left, so you just factor out this, that's just straightforward. And then you're left with 2 minus ikr minus kr squared over r squared times the gradient of r times gradient of r plus the last part of this equation, so the third part of the previous line, which is ik r squared minus r over r squared times the gradient of R. So I just, side note, I want to attract your attention on the fact that the gradient of R is not the same as taking the gradient of R times the gradient of R. So you cannot factor this out. These are two different terms. So this is the equation we want to use when injecting this into the expression of the green tensor as a function of the scalar green function. But we need to manipulate this a little bit more in order to actually be able to make sense of this equation. So we're going to be using two relations that you can demonstrate, or you can find the demonstrations in any mathematical physics textbooks, where the gradient of R is actually equal to R over its norm. Okay, and the second expression we need is actually looking at the gradient of R. And this is giving you this relation between this operator and the unit tensor I and the outer product R. So the outer product of R with itself. So we're not going to demonstrate how we obtain those relations. That's something that can be found in mathematical physics textbooks, or you can actually try to rederive themselves yourself if you want. This is something which is beyond the scope of this demonstration. So using those two relations, what we're going to be doing simply is just using the first one here and injecting this into the first part of the previous equation, and then we're going to use the second one right here and inject that into the second part of the equation. So that basically we get rid of the gradient, the nabla operators. So let's do that, and let's just rewrite straightforwardly what this term is when you make this change. So when you make this change, so you're left with the first term, which is the scalar green function. The parentheses will remain the same, so we have 2 ikr minus k squared r squared over r squared. And then instead of having gradient of R times gradient of R, then we have this R over R twice, so squared. So we take the outer product of R with itself over R squared. And then the second part of this equation, the previous equation, we have the parentheses that will remain the same. And then we have this last term, which is substituted by this bit more complex term where you have the unit tensor and the outer product of vector R with itself over R cubed. So now we can rearrange this a little bit. And what we're going to be doing is fairly simple. So the first thing we need to do is basically isolate the terms and try to factor out some of the elements. So we have this term, which is a function of I, of the unit tensor. So we're gonna just rewrite this term as is, pretty much ik r. So we simplify also by r on the numerator and denominator, and then we have over r squared, and then we have the unit tensor. So that's this first term that we have here. And then the other two terms, you will see that they are a function of R, the product. So we just take this and basically factor out the other product. So we have this other product of R with itself over R4. You will see that we have R4 coming out. And then we basically just put everything else together. So we have 3 minus 3 IKR minus KR squared. So what can be done is actually put this as a function of R2 and reduce this one as R2 if you wish. So that's pretty much it. Now we are closing in close to the end. What we need to do from there is simply inject those things into the actual expression of the green tensor, the dyadic green function. So we can just take back the original expression as a function of the scalar green function, and what we come out with that is just this additional term, this 1 plus, which will be different. That's coming from the unit tensor in the previous expression from the very beginning, and then pretty much we just copy paste everything from the line above. So we have IKR minus 1. And then we don't forget the 1 over k square term from the overall expression. And then we have this tensor. And finally we have this 3 minus 3 IKR minus k square r squared k squared r squared. And then we have this R outer product over R squared. So this is the expression of the dyadic green function, which has been derived from the scalar green function. So now we can do actually a little bit more from there. Try to extract a little bit of physics, something that we've done in chapter 2, a little bit, and something that we're going to be seeing also in chapter 4 on optical interactions. So what we're going to be doing here, starting from this particular expression that we have here, is actually rearranging this a little bit in a sense that what we're going to be doing is just expanding all those terms. So we're going to be expanding those terms a little bit. So we're just going to take the scalar green function from the beginning and expand that. And we're going to rearrange some of the terms a little bit more elegantly to show you a little bit of physics from there. So what we're going to be doing is I'm going to just relabel that G node of R, which is just the scalar green function for simplicity, and then we're gonna just develop this expression. So the dyadic green function is equal to G node of R times the unit vector tensor. That's developing the first term. Then we have G node of R times IKR over k square r square times the unit tensor plus G node of R times the -1. So we have this -1 from the first parenthesis term, so that will show up as negative here over k squared r squared. And then we start developing the second term a little bit. So the second term, we're just going to break down every single element. So we have the 3 over k squared r squared times the outer product of r with itself over r squared. And we have negative 3ikr over k squared r squared times the outer product. And I forgot to mention that this is times g node over r squared times g node. And then the last one is negative g node k squared r squared over k squared r squared times the outer product of r with itself over r squared. So this is very long because we developed all the terms, but there are different things that are actually important. First, we're gonna try to now refactor out some of the terms. So we're not gonna factor out a g node as we've done before, but we're actually gonna look at the dependence of these terms as a function of 1 over kr. So we have this term here as well as this term here that will actually be function of, not function actually of 1 over kr. So this is g node as a function which is multiplied by I, the unit vector, and the second term is actually negative r outer product over r squared. And why? Simply because this dependence over 1 over kr is actually cancelled out. So this one has no dependence over kr. The second term, we're going to take dependence. We're going to have this g node, and then we're going to factor out dependence on I over kr. So how do we do that? So basically this depends over 1 over I kr comes from this guy and coming from this term as well here. Here. So these are the terms that are coming from with the dependence over 1 over kr. So why the kr here cancel out the square on both terms. So we are left with the first term, which is simply 1 over kr I. And then we have the second term, which is a negative sign. Then we have this 3i, so 3 because we factorize the I. And then we have the r other product with r squared. And finally, the last two terms that we have here and here are actually a dependence on 1 over k squared r squared. And that's fairly straightforward. So the first one is negative I, the unit tensor, plus 3 times the outer product of r with itself over r squared. So why we went through all this trouble here to rearrange this? Simply because this shows some physics. So the first term, which is right here, is actually a far field contribution. So this is the far field component of the green tensor, looking at far fields, the electric fields which is far from the source. The last term, which is right here, dependence on 1 over k square r square, is actually a near field term. So this is looking at the electric field in a very close distance, very short distance from the source. So this is a local field. And this last term, which is intermediate in both, which is 1 over kr, is called the intermediate field. So this is the intermediate field. And something which is worth noticing is that this guy, because of the presence of these complex values, so this imaginary number is actually out of phase by 90 degree respect to the far field and the near field.